In this video, we're going to talk about the Pythagorean theorem and how it applies to right triangles. But before we can jump into that, let's review solving quadratics using the square root method. Since this will come up in solving right triangles, we'll need to know how do we take something that's squared and remove that square. And really the answer to that is we're going to be taking the square root. Those work as opposites of each other. The idea being that in general, if you have some variable squared, if you take the square root of it, those two ideas cancel out each other. So all you would be left with is the variable. Now there are some extra rules with that come up in algebra, but quick and dirty, that's what we're doing. To get rid of a square, we take the square root. So, for example, if we wanted to solve this x squared equals 15 and our variable that we're interested in, so we want to get x all alone on one side of the equation, but it's trapped underneath that exponent of 2, then what we need to do is take the square root. And whatever we do on one side, we have to do to the other. So when we do this, x squared, and then we take the square root, we'll have our variable left over. And something that happens in algebra here is when you do this, you really end up with the positive and negative form of that solution. So the positive and negative form a square root of 15. With where we're going in this section with Pythagorean theorem, and in terms of geometry with distances will only be dealing with positives. So I'll keep that plus or minus in there, but in terms of the work that we do in the following problems, we'll only see the positive answers coming out. So we'll have that square root of 15. If you're trying to plug this in as a solution, what can work for typing in an answer is in a lot of formatting like Microsoft Excel and MyOpenMath, if you type in SQRT, that'll represent square root of 15, and that would be an exact solution. If they wanted a rounded solution, and with this video, and typically in general, I'll tell you if we switch. In this video, I'm going to stick to rounding to 2 decimal places, since that's a common form that's used. Sometimes we'll round to 4 because it gives a lot more accuracy, but if we wanted a rounded solution, then what we need to do is fill in that square root of 15 into a calculator. So if I go back to my GeoGebra calculator, what you can see is they have a square root function, or you can type it in like I wrote there, SQRT of 15. You can see it even changed into the notation. So this would be a 3.8729. Again, if we're rounding to 2 decimal places, imagine cutting there after the 7 and then just see whether or not you round up. So because that 2 is a low number, we're going to keep that 7 as it is. So rounded, this would be a 3.87. So whatever solution they want, those would be the 2 options for showing that. All right, so part B here gets a little more complicated in that I want to solve for r. I want to get that all alone on one side of the equation, and I have something adding on. Before I can take the square root of both sides, we want to completely isolate our squared term. We want to just have our variable squared, whatever it is, equals, and then everything else on the other side of the equation, and then we can take the square root. So my first step here, I'm going to subtract 5 from both sides. So then I'll have r squared all alone on one side of the equation, and then 41 minus 5 will leave us with a 36. And now that I have my variable squared equals some number, now we can take the square root and square root. So this will leave me with r all alone on one side of the equation. Technically we have a plus or minus here, and square root of 36 should simplify to a whole number of 6, because 6 squared is 36, so when we take the root, it's just finding that base value under that exponent of 2. With these, you can always check your answer too, like take the 6 and plug it back in. 6 squared plus 5 should equal that 41 there. All right, this last one here, just for solving equations, again, we want to get this t all alone on one side of the equation. So first thing we do is take care of any addition, subtraction. So with that minus 7, We're going to want to add 7 to both sides so that we can get our variable term all alone. So 25t squared equals 49. And then to get our variable really isolated, we want to get rid of that 25. So I'm going to divide by 25, divide by 25. Now, when you're doing work in general with math, we really want to save rounding to the very last step, meaning I'm just going to keep that as a fraction, and I'll show you this in future examples too, of how, like, if we're typing into a calculator, it's better to keep it as exact as possible and not round along the way, because if we round and round and round, the error is really going to compile. So save rounding till the end. And that last step, then we can do rounding, but try to hold off on it until then. So what I mean here is, okay, on the left-hand side, I'll have t squared and 49 over 25, where I can punch that into a calculator and get a decimal. Just for accuracy's sake, I'm going to leave it as 49 over 25 for right now. Then I can take the square root of both sides. So when I go to my calculator, I'm going to plug in the square root of 49 over 25, so plus or minus, and in an exact form, it would be 7/4, or as a decimal, 1.4 exactly. So, all right, so that's the square root method, and when we get to Pythagorean theorem, this will be part of the step that we need to do, which is taking the square root of both sides of the equation. So, the Pythagorean theorem. It's a theorem that's specific to right triangles. It doesn't work for any other triangles. What we need is somewhere in our triangle we'll have a right angle. Now, when we have a right triangle, some components come out. The thing we always want to recognize is, where is the hypotenuse? So the hypotenuse is the longest side length of our right triangle. If you're ever unsure of which side length looks longer, if you find your right angle, which should be clear in your triangle, it's always going to be opposite of it. So if you imagine standing at that right angle and you're looking across the field or wherever you're at, the side length that's across from there that's not intersecting with that right angle, that's your hypotenuse. Then we just call the other side lengths legs. So this would be a leg, this will be a leg. And just for specificity, I'm going to give a little subscript of 1, subscript of 2. It doesn't really matter. It's just going to help when we get our formula out. So when we have a right triangle, there's a property that works with relating our side lengths. Now this property, it tells us that if you take that hypotenuse squared, and I'm just going to write this out in words for us. So the hypotenuse, if we square it, it's going to be exactly equal to the sum of each of the legs squared. Meaning, if we take leg 1 and square it, and add it with the other leg squared, it'll be completely equal. Now, the key piece here is having the hypotenuse squared all alone on one side of the equation, and then adding up the leg squared on the other side. For short, as you've probably seen this formula before, we'd have hypotenuse squared equals leg squared plus other leg squared, and it's just when you grab whatever value you're plugging in for C, it must be the hypotenuse. Must be the longest side length that you're working with. So let's try this out. So let's say we have this triangle right here. We want to make sure it's a right triangle, so you give us a symbol so we know we're good to use the Pythagorean theorem. Then we just want to make sure where is our hypotenuse. So it's going to be side length AB. Again, it's across there. So this would be our hypotenuse. I'm just going to call it C. And that means I have these two legs, A and B. It doesn't matter which is which. Order doesn't matter there. All that matters is we know which side's the hypotenuse. So that means we'll have the hypotenuse squared is equal to leg squared plus other leg squared. And then we're going to start solving. So there's a few ways to do this. We could plug in everything on the right-hand side into the calculator. I'm going to do this a little more complicated just to get you guys the most accurate answers, especially when the side lengths get a little bit more complicated. Where we could simplify that right-hand side, what I want to show you is if it was more complicated and it would almost force you to round a bit, what if we just left it as is? Because the key is that I'm solving for c here, which means I'm going to take the square root of both sides. So what we could do is type into the calculator all of this at once, because I'm going to get c, and basically what I'm going to type into my calculator is square root, and I'll even show you on GeoGebra's calculator, square root of 16 squared plus 24 squared. Oops, and that all got stuck there. That's a good formatting tip. If you're in the exponent, if you just hit the right key, so like your arrow button, if you hit to the right, then it'll bring your number back down, and exponent 2. And then just plugging it all at once, if those were complicated decimals that after you square them, they got more complicated, this is how you could plug it in all at once, and it would give you that exact answer out. And we're going to go ahead and round to 2 decimal places here. So if I cut off at that 4 there, just check what's to the right of it, which is another 4. So rounding, it's just going to stay the same. So this would be a 28.84 for a solution. And then grab your units if they tell you what they are, which in this case is centimeters. So that's an application of our Pythagorean theorem. Let's try another one. With this one, so you can see our right angle there. So if we look across the way, this is our hypotenuse. So in this case, we actually know what the hypotenuse is. We know one of the legs. We don't know the other leg. So with this, our unknown changes, and you want to be careful because a common mistake here is to just always put the hypotenuse as the unknown, but sometimes you know the hypotenuse. So what this is going to look like is we'll have the hypotenuse squared, which we actually have a numerical value for it, 7.125 squared, equals leg squared plus the other leg squared, which one of those is our unknown. So this is what our formula would look like. So these are kind of the 2 cases. Either your hypotenuse is unknown or a leg is unknown. You'll always have one piece, or not always, but sometimes you'll have just one piece missing, and just depends on what side of the equation it's going in. Now this is the case where if you try to start squaring things, you might have to round, and then that gets messy and introduces a lot of error. So let's again try this without doing any rounding in the process. So the key is I want to get b all alone on one side of the equation. So I have the 6.75 squared adding on to it, so I need to subtract that from both sides. So that means on the left-hand side of the equation, in kind of a long form, I have the 7.125 squared, and we're subtracting 6.75 squared. Equals, and then on the right hand side that all cancels out, so all we have is b squared. And then I'm going to take the square root of both sides. So we're solving, and we'll be getting b here, and then this is a case where I would just type all of this into the calculator. Square root of 7.125 squared minus 6.75 squared all at once, and round to 2 decimal places, and that should be a 2.28. In this case, it's inches. So those are the 2 scenarios for solving with the Pythagorean theorem, either solving for a leg or solving for hypotenuse. Let's look at an application of this. So we have Aisha, usually walks home around the edges of a local park. One side of the park is 2.1 miles and the other is 1.4 miles. How much distance would she save? There's a little word missing there. Would she save to the nearest 1/10 of a mile if she cut across the park diagonally? So if I draw a little picture here, what we're going to do is think about this diagonal path across this rectangular park. So we're going to have, let's say there's Aisha, here's her home, and what she usually does goes along the outside. so at 2.1 miles. And then we'll assume this is rectangular, so we're going to have a right angle there, and then 1.4 miles. So her original path of how far she has to walk would just be that 2.1 plus the 1.4. So usually she has to walk 3.5 miles total. So what we want to see is what's the length of this diagonal here, and that's where we can bring in the Pythagorean theorem. So we have our right angle, our unknown is the hypotenuse. So setting up our Pythagorean theorem, we're going to have our unknown squared, so hypotenuse squared equals 2.1 squared plus 1.4 squared. And solving, we just need to take the square root of both sides. So we're going to take the square root, plug all that into the calculator, and they did specify rounding rule here, nearest tenth of a mile. So that's 1 decimal place. So it's going to be a little different than what we've been doing previously in this video, but rounding rules are the same. So it should round to 2.5 miles. So in terms of what she would save, you just want to think of the difference between those two. It would be 1 mile shorter. So that's an application of our Pythagorean theorem and how to use it for different scenarios.